our last presentation will be done by Gaël, Delbary, and Aurélien Cedeyn. Gaël has been working at CEA for 14 years in the HPC division. During the first 7 years, he was a system administrator in Linux Windows environment. In 2015, he joined the HPC storage team as a software administrator. And for the last 5 years, he has been in charge of the next storage architecture for supercomputers, research and development on HPC storage platforms, and L3 system support on storage clusters. And Aurélien has been working at CEA for 12 years in the HPC division. During the first 11 years, he was an HPC system administrator. End of 2021, he joined the HPC storage team as a storage administrator and works on storage optimization and debugging. He also is in charge of the in-house Linux distribution at CEA, Océan.
Thank you, Guillaume. It's again me, sorry. So we are going to talk about the talking of Lustre Filesystem at scale around 20,000 of clients. We haven't synced with Sebastian Peszczowski, but it's a continuation of its presentation. In this presentation, you will have the impact when you don't set the right tuning, with the S tunings. The agenda is we will do a quick seat update, and after that, we will explain the context case study and the different parts where we did some tunings. It's like a horse riding race, if I can say. I don't know if it's a good sentence, but you try to think something, so it's fixed. But like Sebastian said, you have another issue after that. So yeah, it's a life. Anyway, a quick seat update. At CEA, we have still 2 production compute centers, one for defense and one for European research. We have also one other, which is the compute center of R&D, which is pretty useful when we want to test, to bench hardware and software stack. Some numbers about the compute power we have on the defense center. We are about 40 petaflops and we have 20,000 clients. But they share the same storage approach with a similar design. In fact, it's the same architecture. Why? Because it is the same team, of course, so it's easy to administrate, to manage. And also it's for a user perspective. You see, it's a pretty old picture here. It was done by Stefan, so it's pretty old, but it's still true today. The name of supercomputers have evolved. We have many, but it's still true. We have a data-centric approach where we put the storage at the middle place. Okay. Now we are running Lustre 2.12.9++, of course, with a Lustre HSM version. We plan to upgrade to 2.15 in Q2 or Q3 next year. Some numbers, you have some numbers in throughput, which is not pretty interesting here because anybody can do some high numbers. You can do this number with HDD drive or SSD. It's just a question of numbers. But at CA we have recently IOPS workload and requirements. As you know, on the defense parts, we have a Lustre Filesystem in random writes around 20,000 millions of IOPS. So, I am sorry, we go back to past. Last year, Q3, Q4 2021, we had a new supercomputer, which code name is Exa1, a big one. But of course, this node would like to mount our Lustre HSM file system. These new supercomputers come from a new interconnect, the Atos Big Psi, with a custom LND, a specific LND. To connect the compute nodes to the servers, Lustre servers, we have 60 routers. So it adds 7,000 of clients plus the current we add. A quick picture of what we have. You have on the left the last current situation where we have 12,000 of nodes which mount the Lustre Filesystem interconnected by 200 net routers. On the server side, we have 4 metadata servers and 40 OSS. But on one OSS, we have many targeted for a total of 484 OSTs. Again, on the right, you have our new supercomputer. I would like to mount this file system. To do that, it goes through 60 net routers. Okay, what we know, we have 20,000 clients in total. Have you seen 3 supercomputers with the same Lustre FS? So we have to be careful, because if we have an issue of one file system, all of these supercomputers are hung. Okay, we have heterogeneous router configuration due to the kind of interconnection we have. We have Big Psi V1, Big Psi V2, Connect IB, Connect X4, Connect X6. Also, we have Lustre servers with HA configuration. These servers are all virtual machines. Okay, what we know. Lustre is scaled pretty well, up to 10,000 of clients. If you follow the Lustre manual, you can have a well file system. But we have seen that a long time ago, in 2012, created some issues with large supercomputers. It's an excellent paper which explains how the OBDPing is working. Okay, we will see what is it after. The last point is the new interconnect is pretty young. In fact, at CA, we have the luck to test the new interconnect. So we had some issues on large scale. Right now, it is fixed. So, gave us a try to mount the FS. All the prediction is working. Okay, it's not true. We are in a maintenance slot, but anyway. What we do is to mount all nodes at the same time. Okay, the result was pretty cool. We have seen many target disconnection on already mounted client. But what we can say, we could mount it successfully the FS, but in step of 500 client. Okay. But we need to understand what is going on when we do this and why we cannot mount as soon as clients. What we have seen during this, it's time, we have seen many net credit starvation on routers and servers. We have the memory which increased by 50%, which is pretty huge. And we've seen many small RPC on the MDS NGS node, about 180,000 RPC per second. A quick sum up, but you have seen on the Sebastian talk, it's just when you are working in Lustre, you have to know exactly in which layer you are working and you are rely on. On this topic, we will talk about LNAT, the point-to-point communication between client and router, between router and server, and of course also with PTL RPC, which is an end-to-end communication protocol from client to server. On the left, there is the picture which is extracted from LAD 15 from Chris on talk. This talk was amazing and pretty useful when you want to understand how credit are working in Lustre. So, first analysis. What we can think is that, in fact, we have not enough resources on server side to absorb the client activity. You can monitor this easily. Sorry, James, it's the big face. With the syskernel debug and net peers. What you see here, you have the line in bold. You have to highlight the bold value and the mean. The mean value is the low water mark. So sometimes, perhaps in your configuration, in your system, you will see some minus value, but it needs interpretation and analysis to understand why it's low. What I want to say is that it's not because you have a minus value, it means that you have an issue, okay? But when you see the last column, the Q column, it means that you enqueue messages. In this kind, when you have this both value and the low watermark have 5 digits, it means something goes wrong. Okay, so first approach, of course, we have not enough credit to absorb the amount request. Just to sum up, you have understood when you are doing LDMR communication, you write some information on the remote memory of one node. You don't care, you don't know if you lose a packet and so on. So you have to rely on something, on a protocol. In LNet, the credits is the throttling mechanism. It's like, for people which know TCP, like TCP congestion windows and the algorithm they are relating with the kind of mechanism. A quick notice, you have understood in the presentation of Sébastien, peer credits is different from credits. And what we can sum up about the peer credits, it's a max in-flight and net messages allow for a peer. And there is a difference with the RPC, max RPC in-flight, okay? We are not on the same layers. Okay, what we have done at CA is that we adjust the higher value of credits we could achieve with some restriction. We are limited on the MOFET version. We are stuck on the 4.7.3 version because we have Connect IB cards. And this version of MOFET plus some Connectix firmware version, we are not able to go through 42. Okay, there is an exception on the client side where we couldn't increase the value of credit above 32. There is an LND limitation. Okay, about the credits, the default is 256. It's the same rule of thumb Sébastien presents. We compute the credits, the value is peer credits by the number of peer you've seen on the net layer. A quick remark, if you want to check how many credits you have, the value is divided by CPT. Okay, we are going to see what is a CPT after that, but be careful in the code, there is a minimum value of 64 credits per CPT. Okay, you have understood that you have to compute the number of credits on the routers, thanks to Sébastien, but we did another thing, we did some trial, and we monitor the credit consumption during worst case we have in the compute centers, and we just set up the right value on the router. Okay, it was pretty cool with this kind of modification. We can parallel mount the 7,000 clients successfully, but we have seen some disconnection on some parts, some clients. We have still few credit salvation, but we are not on 5 digits, only 3 digits, which is not a huge value. And good news, other clusters are fine. Okay. It was amazing, but after this modification, we had a kind of job which breaks 2,000 nodes. That was a job issue. But the impact of this is that we have a kind of storm, the baby storm, remember, of big size interconnect instability, where some clients are able to communicate, but not. After some piece of time, a bit, I'm talking not in netlet, and I am on the layer of the network communication. So the result is we have out of memory on routers and servers, and other computers are stuck. So it's a bit catastrophic issue. And when we monitor the number of messages we have between routers and servers, we are close to 8 million of RPC per second. How can we handle this? I think Aurélien is going to answer to this question.
So yes, to handle this issue with the 8 million of RPC per second, the first approach was to understand why we cannot digest or absorb this amount of RPC. So we are first looking for the CPU partition table, which is the CPT, just like Gaël said before. So to monitor that and to try to reproduce this, we use the LNet self-test tools, which is a good tool to try that. And we see a limitation on IB servers and routers about 180 K RPC per second. So there is an issue here with a suboptimal CPU load distribution because some of them are about 90% of usage and some others just about 30%. So with digging this issue, we hit the LU14676, which is about the hashing function between two peers in the LNet protocol. So given that, the idea is to adjust and to have a better number of CPU partition tables to handle the more and more requests. So here you have the configuration we put in production at CA with a CPU configuration of 12 cores and 1 NUMA node. As you can see, we just use 11 of CPUs and we let one for the system. So with this configuration, we add a big boost, so like by 10 RPC absorption per server. So it's a good news. But we still have many RPC on MDS and MGS during the storm of connection, during the mount process of the 20K nodes. So we add some clues. So first of all, we want to analyze the difference of the MGS and the MDS traffic. So we separate the both and have a better analysis of this situation. So we can monitor these two traffic and show what is going on this different connection. So we can monitor the different CPU partition configuration by the two ways. The first is the LNetCTL netshow-v, which will use like a client or the tool itself, and we have the direct access to the CPU partition table in the syskernel debug LNet file. So by increasing the CPU partition table, the trade-off is that we gain memory usage on each server, which can lead some problems. So we still have, we absorb now a lot of RPC, but why have we this RPC? Because it's really a lot of little message which cause our root problem. So we still want to know what is going on. So what we didn't say before, yes, we did that. The job produced some out of memory on our servers. So with our tuning, we just have a little one out of memory exception on some server in some cases. So we still continue to analyze this, and we try to understand the RPC storms. What we analyze is that we just have high priority RPC. It's just this storm of high priority RPC which leads to the out of memory on our servers. So when have we the high priority RPC? Most of the most common case, and with an unstable network, we have the overlapping process, which is the main RPC we see. The overlapping process will have different function. One is to give health status for the server to the client and to the client for the server in the both ways. Overlapping are regularly sent like a keep alive status to know if a server is alive, to know if a client is alive. And really regularly, and at the scale of 20K nodes, it goes a lot. It can be a lot of traffic. And another high priority and overlapping process can be sent is when a client has no more connection, no more credit, or has a network trouble. He'll try to resend immediately the connection, and so on and so on. So with the number of clients, it's really a huge traffic which leads to a net floodings with RPC, with overlapping and HP RPC network package. So we profile, to understand why we have this deconnection, we profile the user workload. So it's a quite big workload with an IOR, with one file per process, with 1K nodes. So multiplied by the number of process, it's really a big workload, which is not really, it's hard to absorb, let's say. And what we can say is that because of that, the OST-IO service on the servers, on the OST, was the one who leads to the out of memory. So we have two solutions two ways to fix this. Is first to try to fix something in the user code, and the other one is to reduce the overlapping burst, which is what we said before. So the solution is to use adaptive timeout, and that's a way that Sebastian talked just before. What we are sure is that because of the network issue and reconnection, the storm comes from that. Just without doing anything on the file system, we can have this kind of behavior. So for RPC timeout, Lustre relies on adaptive timeout, and the best practice talk about AT max, but not often of AT min, which is the one we choose to address this issue. So Sebastian talked about that, but globally, a value of 0 for AT min means for the client, I want to resend immediately a packet which was not sent, and this is why we have this storm. So tuning this value to a good value will solve our problem, in fact. So relying on our LNet configuration, we can compute the good value of the AT-min parameters, and this will say to the client, just wait. I know this, you cannot send your packet, but wait just a few seconds, and if you retry after that, maybe everything will go back better. So that's what we compute. So AT-min is the retry count +1 by the transaction timeout plus a little piece of processing time. So at CA we choose to set up AT-min to 55, which solve, in fact, the storm. So, to conclude and to sum up this presentation, we go deeper on this problem, and we simulated 80K parallel months on client to see if this kind of configuration can be robust over the time. And so what we can say is that it takes 30 seconds to mount. Some credit starvation, we can observe some credit starvations, but everything goes well, in fact. We don't have any out of memory, and everything is quite stable. On our production, the 20K clients are successfully mounted and are used in production. The bad behavior of our user can be stopped, so no more OM on our production. On our production. Now, luckily, we have a new BXI version, which are a lot more stable now. So everything goes very well now. So yes, what we don't say before is that we had the out of memory was produced by some calls like the PTLRPC GROW rect buffers, which was the function which allocates the memory, and this is the deep inside of the OM. We also have some TBF configuration to limit bad user request and workload. And so to conclude, we have to have a large Lustre and stable file system, we need to tune correctly the LNet credits, to have a good CPT configuration to absorb most of the traffic, and a good adaptive timeout will help if there is some network issues. Thank you. If you have questions.
Thank you, Aurélien and Gaël. Any question for Aurélien and Gaël? With these two last talks, you have everything to tune. Yes, Andres.
So the AT-min, being too small, I mean, that's something we've seen at a few sites, but, haven't had time to work on. There is an open ticket. I don't know if you have any interest, to what we would, I've been thinking is having, because the server is the only one that knows, how many clients are connected. Each of the clients don't know that, but AT-min is important on the clients, and have some, mechanism for the servers to, say, oh, as the number of mounted clients increase, please increase the AT-min. And it doesn't have to be instantaneous because, you don't need it right away, but if the clients are pinging, if they would get some update, right, that says, or through adaptive timeouts that say, increase your AT-min, because on a 20,000, client cluster, you have to be more tolerant than, we also have to work in, the 20 client kind of financial or whatever, where they don't want to wait a minute for it to even try to recover an RPC, right? And so I don't know if that's something you'd be interested to work on.
Yeah, I think so. Andreas, is it the ticket from Patrick? Yeah. Okay. Okay.
Yeah, thank you, Gaël, Aurélien.
Thank you.
Thank you.